and you hear me say this a million times because I do try to spiral in these things quite frequently. We've done a lot of conditional probability already. The only thing you haven't seen officially is the formula that you get on the AP exam. There are two formulas that come from the basic probability unit. The first one that you get on the formula chart, just to remind you so that you don't feel like you have to remember it. This also will be beneficial as you start to work through your test review. You get the general addition rule, which is the OR. Anytime you're doing ORs, you're adding. Anytime you're doing ANDs, you're multiplying. So this would be the probability of A plus the probability of B minus the probability of A and B. So this was one of the problems where if I had a Venn diagram and there was an overlap between the two events, if I take all of A and all of B, that overlap gets counted twice. And we don't want to count it twice, which is why we subtract one time. Just to kind of go in and review a little bit more, just because you guys are coming off of a 4-day weekend and we'll see each other one day and then you're gone again. If two events are mutually exclusive, just because of the addition rule, there were times where you had to subtract A and B and times where you didn't. If it was mutually exclusive, that meant the probability of A and B was equal to 0. So basically there was no overlap at all. So when I had independent events, there was nothing where they happened together. Therefore, we didn't have to actually write out subtracting 0. But those are kind of the main topics that we've covered so far. The general multiplication rule was just if I have two things that need to happen, I need to take both of those individual probabilities and multiply them together. So whenever we talked about the general multiplication rule, we said that if events were dependent, that meant that the second probability changed depending on the first. So think about the deck of cards, where if I'm trying to see the probability of pulling a black card, it's 26 out of 52. And if I've removed that card from the deck, now the probability of a black card has dropped to 25 out of 51. So those were dependent events where that second probability that you're looking at, that is changed based on what happened in the first event. So this formula that you're seeing like highlighted in orange isn't one that they give you on the AP exam directly, but it's one that you can kind of adapt from the conditional probability formula that they do give you. So the conditional probability is the probability of A given B is equal to the probability of A and B over the probability of B. Now, one thing about this conditional probability is we can take it and we can adapt it to give us the general multiplication rule. Notice that I have the probability of A and B in this formula, which is what the general multiplication rule is helping you find. And if I wanted to go and I wanted to take this to just getting A and B by itself, I would come in and I would multiply both sides by the probability of B. And what you'll see is, and I know it looks backwards just because of the way we wrote A given B. If I wrote B given A, I'd get the exact same formula, but that's not how it is on the AP exam. We end up with the general multiplication rule. So if you're someone who's like, I need to memorize this because I don't have it on my formula chart, you can, but you really don't have to, because what you do get, you get this formula here. You can kind of adapt it to be the general multiplication rule on formula chart. So those are the two that you get, the addition and the conditional. The conditional can be changed so that you have the multiplication rule. Now, there are pros and cons to the formula, as there are in any kind of situation. I personally think that in situations where they give you a table you really don't want to think of the formula. We did conditional probabilities like way back in Unit 1 when we were looking at categorical variables and trying to see the frequency of them occurring. A conditional probability in this unit is the same thing as a conditional probability in Unit 1, where we were taking in our case, when we did it, we were taking a single cell over a row or column total. So this is still a conditional probability. And I'll show you how the formula still works even when we think of it like this. But in my experience, if you have a table, don't overthink it. Look at it in the way we've been looking at it already. Don't try to force the formula onto these types of questions because sometimes it'll confuse you a little more than it should. All a conditional probability is doing is changing the sample space. So instead of it being the whole entire, in this case, they're showing you a Venn diagram, it kind of drops down and it shrinks the sample space to the given event. And one thing I will point out in the formula itself, whenever you have your given, you always write it second, and then it'll always become your denominator. So anytime you have, if we select a senior, what is the probability? It's a boy. The if we select a senior is our condition, so that's going to become my denominator, and I look at that event only, and I see how many of them are boys. So again, don't overthink it when it comes to tables. So I'm going to kind of approach example 1 in both ways. I'm going to show you how the formula will work, and then I'm going to talk about how we probably should do it with just basic fractions. So I have women, I believe, and I have hair color and I have eye color. We have a question asking if we select a woman and find that she has brown hair. So this is going to be my condition. So this needs to be, when I go to write my probability statement, the thing that I write second. If we select a woman and find that she has brown hair, what is the probability that she will also have hazel eyes? So when I go in and write out my starting statement, my given is going to be brown hair. My actual point of interest is, does she have hazel eyes? So that is going to be what ends up getting written first. And as much as I would love to tell you the order you write these in does not matter, College Board will care. So make sure that anytime you have your condition statement, that is what you are writing second. So hazel eyes is our condition. Now I'm going to kind of show you the formula just to show you what it would look like with our specific information filled in. We are taking the entire sample space and we are shrinking it down to the probability of brown hair. And what I'm actually interested in is the probability of, and it's going to be an and, I guess I did not give myself enough room, brown hair and hazel eyes. Hazel eyes. Let's see if I can move this. Okay, now remember, in a table, the row or column total is a marginal frequency. So in my particular example, I want all of the people who have brown hair. So I go to hair color, I go to brown, I look at the total. It seems like there's 143. So I'm going to put 143 as my denominator because I'm shrinking my sample space from all 313 people down to the 143 that have brown hair. And then I'm interested in, of those 143 people, how many of them have hazel eyes? I get 29. I will ask on your test that you convert to either a decimal or a percentage. I don't care what you pick. I'm just going to keep it at a proportion, a decimal value. And I will ask that you round to 4 decimal places. So there are 3 things that you need to kind of get full credit if this were an FRQ question. You need your probability statement, which is my very first piece that I wrote. I don't necessarily need that second part where you write out the information in the formula, because you may not even be using the formula. You may just go look at the table and be like, okay, that's 29 out of 143 and move on. Completely fine. So I don't need the second part, but I do need your fraction setup and your decimal or percentage answer, whichever one you prefer. So that's kind of what we'll be looking for on the test. So now that we have one down, if we select a woman and find that she has brown eyes, what is the probability that she will also have black hair? So I'm going in, and my condition is everyone with brown eyes. So probability, and I'm going to do the same thing. I'm going to do my given. Condition is brown eyes. And my actual variable of interest is black hair. And so again, I'm going to use the formula. You don't have to, but I just want to show you that it does work even when you apply it in these situations. I'm doing the probability of brown eyes, which is shrinking my sample space from all of the people to only the people who have brown eyes. And I'm going in and I'm doing brown eyes and black hair. And so the total number of people that have brown eyes, if I look at my table, there are 122 people total. And the number of them that have black hair is 36. So all I have to do is 36 out of 122. So this is one of those situations where I don't think that approaching it with the formula is entirely beneficial to you. There are times where they don't give you tables. They just give you values. They'll say the probability of someone having brown eyes is whatever 122 out of 143 is. And the probability of someone having brown eyes and black hair is this. What's the condition? Like, what is the given you pick somebody with this? What is the probability of this? So sometimes in the questions, they don't give you actual counts. They'll just give you percentages, but you'll still plug them in exactly the same way. The and on the top, the condition on the bottom. So let's go in. Let's talk about one other way that we use conditional probabilities, because we've already discussed a lot of them in all of our other notes. So one little thing, if we draw two cards with replacement, we know that those events are independent. Basically, the probabilities will stay the same. They remain consistent. Nothing really changes. If I do something without replacement, that turns into a dependent situation where I run into the issue of the probabilities start to alter. So I have to remember to decrease them, especially in things where you're pulling multiple people out. That overall total changes. And if you're pulling out people that you're interested in, the numerator changes. Now, in the real world, we have to kind of determine if two events are independent or dependent. Do they have a relationship? Do they not? So we go in and we try to prove independence in two ways. One way is we can use the conditional probability rule, and you're basically verifying even if I go in and I select a subgroup or I select a different event that's happening. Even if I do that, we're trying to see if the probability of A remains the same. If it remains the same, if this is true, the left side is equal to the right side, they are independent. Now, in another way, one of the rules we talked about in general multiplication was if they're independent, those probabilities don't change. Like I don't have an A given B. And so if two events are independent, you can also check it by doing A and B is equal to the probability of A times the probability of B. College Board does not care which one you use. If they are independent events, no matter which one you choose, no matter what order you choose, both situations should be true. If they are not independent, if they're dependent variables, you should see both of them ending up being false. It's not like one is going to contradict the other. It's not like you have to check both just to be sure, unless you're like worried your math is wrong. But it does not matter which version you like the best, as long as you know one of them. The only other thing I will kind of say here is if you do choose the probability of doing the conditional, it doesn't matter which one you pick first. You could have also checked probability of B and B given A, and you should still see that these probabilities don't alter, and therefore they are independent. So unless, and I've never seen a question where they've told you to directly check in this order, you can kind of pick and choose which one you want to do. So let's go ahead. I'm going to actually work through both versions just so you see that they both come to the same conclusion. On your actual paper, if you are doing this, you don't have to check both. You only have to do one. So I have two categorical variables, basically what type of produce and how many packages are purchased based on whether it is fresh or frozen vegetables. So I have our blueberries and fresh independent. So to save myself from having to write this a million different times, I'm going to call B blueberries and I'm going to call FH fresh. And I'll use FN for frozen just to make life a little bit easier. So the first way I'm going to do it is with the conditional probability. So I'm going to check, is the probability of blueberries equal to the probability of blueberries given fresh? And when you're verifying this, you want to make sure that you're always writing the same variable first. Because I can check fresh and fresh given blueberries, but I just have to make sure that I'm pairing it up correctly. Now, going to the table, I'm not going to overthink this. For blueberries, there are 56 total. So I'm going to have 56 out of 140. And when I have a conditional probability, the denominator is going to change to the given condition. And so since my given condition is I only want to focus on fresh fruit, I'm going to have a denominator of 50 instead of a denominator of 140. And there are 20 blueberries in the column specifically for fresh produce. Now, just to relate this back really quickly, you're still doing the probability of B and fresh over the probability of, probability of fresh. So I still did the conditional probability. It's just you don't always have to write that out. You really don't have to write it out ever, but then we go in and I get 0.4 and I get 0.4 because 2 over 5. And so since these are equal to each other, we would say blueberries and fresh produce are independent. Now, just to kind of go in and do FRQ thinking, if you are checking this, don't just do it in your calculator and be like, yeah, they're independent. If it's an FRQ question, you have to show your work. You have to set up, what are you setting equal to each other? You set up your fractions, give me your decimals, and then answer the question. It can't just be like a yes, they are independent, no, they are not answer. Anytime you are doing FRQs, you have to have support for why you are choosing to say what you are saying. Now, I'm going to show you the other way. Again, the method you prefer is completely up to you. This would be if I'm checking the probability of blueberries and fresh. If they are independent, the probability of blueberries times the probability of fresh should be equivalent to the and statement. So blueberries and fresh, if I go up to my table, that is these 20 single cell values, so 20 out of 140, because there's no conditionals in this case. It is just going and doing single individual probability events. Probability of blueberries, there are 56 out of 140. And probabilities of fresh produce, there are 50 out of 140. And what you'll see when I go in and multiply these things, I end up getting the same probability. Now, it's not going to be the same probability as the other method. I know some people kind of get caught up on that and they think that they both have to total to the same thing. They do not. The only thing is that they have to match each other. So I get 0.1429 and 0.1429. And so I would literally say the same thing. Say same thing. Blueberries and fresh produce are independent. So pick the one you like. Know that one. I don't care which one you prefer, but either way would work and either way would be true if you had to go in and verify independence. So now that we've shown two that are independent, let's go ahead and look at one that isn't independent. We have avocados and we have frozen produce, yeah. So I'm going to go ahead and be very different and say A is going to represent avocados and I'm going to say FN is going to represent frozen. Is there a method we prefer, left or right? Left, okay. So I'm going to go in. Probability of avocados is equal to the probability of avocados given frozen. And so all I have to do, and again, you don't have to write out the conditional probability formula. I go to my table, I look at how many avocados there are. It looks like there's 24. So 24 out of 140. And then I go to my table, I look at how many frozen produce packages there are. There's 90. And of those 90 frozen produce packages, 15 of them are avocados. And so all I have to do is go in and verify, are these two probabilities the same? I would say be careful and just double check in your calculator because I know some of us are really good at fractions. I'm not one of those people. So I will always still plug in and see, does the left side equal to the right side? It has to be exact. It can't be something where, well, if I rounded to the second digit, like it would be the same. Can I still say they're independent? They have to be exact matches for each other. So since these do not match each other, we would say avocados and frozen produce are, you can say not independent or you can say dependent. I'm just going to be politically correct and say not independent. There are cases where I will tell you, like, we can't say that because we don't know for sure. But in this case, it wouldn't be one of those big, huge deals. Okay. That kind of wraps up, kind of somewhat, but not really, conditional probabilities. The next thing I'm going to talk about is one of those other optional things you can do to help you with these probability questions. As you probably have kind of found out over the course of the last 3 days, it seems pretty simple and straightforward. And then you go and read the math lab questions and you're like, what the heck are they even asking me to do? So this is one of those where I highly, highly recommend you actually use it, because going about it in just the formula method doesn't always help. Sometimes it gets to be a little overwhelming, especially because they give you a ton of information. So a tree diagram is really, really helpful for conditional events, because when we have these tree diagrams, and if you're wondering, like, what is a tree diagram? It's basically where you go in, you have your branches, and then you branch off again and again, and then you may branch off again. But all of these tree diagrams represent conditional probabilities. If this happens, then that happens. So one of the things that we have to consider is all of these are and statements. If you select a senior and they are a girl, like that is like a conditional, not conditional, but like both things have to happen at the same time. So whenever you read a question and you start going through it and they're like, okay, it could be this person 5% of the time. It could be that person 20% of the time. And if it's that person, they could do this 15% of the time. It's going to look really, really overwhelming with information. If you see that, it's usually a good indicator that, hey, maybe I need to organize this by using a tree diagram. So in this particular question, they're talking about electrical connectors for a home entertainment system. And they go in and they say the company prefers to use supplier A because only 2% of their connectors prove to be defective. Okay, cool. Doesn't seem overwhelming. And then they go in and they're like, well, but supplier A can only deliver 55% of the connectors, and then supplier B can deliver 40. As soon as you start seeing like all of this information being thrown at you, probably going to be something that's beneficial for a tree diagram. So what a lot of people get confused on is, what do I start off with? Like, what is like my first branch? What's my second? How do I know what goes first and second? I usually say think logically. Before I get to the point where a part is defective, I have to actually have the part from the supplier. So I would think that the supplier that we use is what's going to come first. So in this case, there's 3. So we're going to have supplier A, supplier B, supplier C. So A, B, C. And they say in the question that they use supplier A 55% of the time, they use supplier B 40% of the time, and the rest come from supplier C. So one little note here is, every single time you go in and you start branching off, those branches have to total to 100%. So if I have 55 come from A, if I have 40 come from B, that's 95% so far. So that means 5% have to come from C. So every single time you branch, it has to total to 1. So they don't always give you all of the information, but they give you enough to figure out what you need to find. And then each supplier themselves, they have either the part is going to work or it's going to be defective. So it's going to work or it's going to be defective. It's going to work or it's going to be defective. Okay, so they say they like to use supplier A because only 2% prove to be defective. So I know if I go to supplier A, 2% of the electrical connectors are defective. And because every single time we branch, it has to add to 1 for it to work, we would have it 98% of the time, because in total has to add to 1. And it's not like every single, if you think of it as columns, have to add to 1. It's every single time you start to branch off. And so they then say defective connectors from B and C are 4% and 5% respectively. Basically means the order you read it in is the order you should write it in. So 4% from B, 5% from C, which means 96% work for B and 95% work for C. Now, here's just a Miss Martinez tidbit. I will sometimes look at my question and I'll be like, okay, are they asking me one thing or are they asking me 4 things? If they're going to ask me multiple things, one of the things that I will do is every single pathway that you take is an and statement. So if I wanted to, for instance, go in and say, okay, what is the probability of selecting supplier A and it works? Every single one of these pathways is a multiplication rule. So if I wanted to write it out, and this isn't what I would write every single time, this would be the probability of it being A and it works, which means we take 0.55 times 0.98 and we get 0.55, 0.98, 0.539. So every single one of these, all 6, have a multiplication rule tied into selecting that particular outcome. So it's A and defective, B and works, B and defective, C and works, C and defective. Now, I don't write what I have up there every single time. A lot of the time, I'll just come in and I'll write what the multiplication is just to save myself some brain power in the end, because I will tell you a lot of what you're going to use your brain for on this type of question is like, what are they asking me to do? Like, what's going on? And so you don't want to worry about like the multiplying and the like continuing and finding out what that particular value is, because if you get it all done pretty early on, you're just going in and you're referencing numbers. Now, one thing about College Board and grading, if you have a tree diagram on your paper and you pull values from your tree diagram, like considering the fact that you wrote them down, like if you wrote the green part, they don't make you show work in the question. They will look at your tree diagram as your work. So I will show you in some of these, I don't have to actually write out what I'm multiplying because I'm pulling it directly from my tree. So the first question that they ask me is they say, what is the probability that you use supplier B? So I'm going in and then I'm using supplier B and the connector is defective. So probability of B and defective. And so in this case, all I have to do is look at my tree diagram, go to connector B, go to the branch that says defective, look at what number I got, and I said that that was 0.016. And that would be enough, given that you have the tree diagram on your paper and it's written out and multiplied. Now, if you did not do the tree diagram way, it's not the end of the world. Again, this is an option. It's not a requirement, at least for the AP exam. I would have to go in and show that I took the multiplying from connector B and the multiplying from that part being defective. And this would be my work with no tree diagram. So there are ways to approach this. Now, I will say it makes it a lot easier to have a visual representation, but it's not necessary. It's not like you have to have it or you're never going to get the question right. It's just you're going to be more formula based than you would be if you're just looking at your drawing. Okay, what is the probability that you find a connector is defective? So, probability of defective. Now, the one thing that we have to consider is the fact that there are 3 different branches that result in a defective part. And that's what a lot of people miss. If I go in and I look at my tree diagram, I have a branch where it's defective here. Oops. There we go. Defective here, and defective here. So if I want a defective part in the end, I have to take all 3 of these probabilities and I have to add them together. So I'm going to take the 0.011, the 0.016, and the 0.0025 and combine all of those things because those are all defective parts. So I'm going to say 0.011 plus 0.016 plus 0.0025 is equal to 0.0295. Now, again, just to show you that you don't have to do it that way, if you wanted to do this without a tree diagram, you would have to go in and show the multiplying for each of these scenarios. So I would have to say like 0.55 times 0.02 plus 0.40 times 0.04 plus 0.05 times 0.05. And that would be my work without the tree diagram. So again, you don't have to do it, but I will say a lot of people, it kind of gets overwhelming when you have to consider all different possibilities and you haven't drawn out all of the possibilities, because it's kind of like you're trying to keep it in your head of what outcomes result in this. Now, for the conditional, given that the component is defective, so given that it's defective, so that is going to be my condition. What is the probability that it came from supplier A? So probability of A given defective. And a lot of the time, especially in FRQs, you'll find that they'll ask you questions where you've already found a piece of it. So in our case, if I were to do this in formula thinking, probability and defective over the probability of a defective part, we found defective already. In part B, we said that probability is 0.0295. So I'm just going to go in and say 0.0295. That's my denominator. And the nice thing about College Board and their grading system is even if you got part B wrong, even if you're like, I don't know what it is, or you rounded wrong and you said 0.295 instead of 0.0295, you'll lose points for part B because it's not correct. But if you use it in part C with that incorrect value, they will still give you full credit for part C because you didn't know that you were wrong, but you went on and you did what you were supposed to do with that number and you got your probability. So the other thing is A and defective, which from my tree diagram is 0.011. So I'm going to go in, I'm going to divide these two things, and I'm going to get 0.3729. And what you'll kind of see if I didn't have these things written out on my tree diagram, I would be doing these multiplications every single time I'm answering a question, which eats into FRQ time, especially if it's what you're doing on the AP exam. So I personally do think that it's beneficial to you to write out a tree diagram for these questions. Now, you can't always use a tree diagram, but if you have things where like, if it's this person, that person, this person, and then this person has this probability and this person has this probability, it's usually, you'll know when you read a question if it's one of these types. It'll be pretty obvious. Now, the last thing I'm going to talk about is it's kind of a niche, like I'm going to cover it because it could show up and I don't want it to be confusing if it does show up. Whenever they do these types of things, sometimes they'll ask you about taking a test and it being positive or negative, whether it's being sick or whatever the context may be. It's a potential of what could happen. So I have a person has probability a person has a particular virus is 1 out of 250. So in my making of my tree diagram, either they're going to have the virus or they're not. Again, think logically. What would come first? Would I be taking a test for if I have a virus, or would I have the virus first? Like, usually that happens before you get your results. So kind of logical thinking. They say it is 1 out of 250, which I'm going to just go ahead and write as 0.00. I believe it's 2 zeros. Yeah, 004. So if I have 0.004 chance of having the virus, that means I have a 0.996 chance of not having the virus. And then you go on and you take the test. And either the test is going to show that you are positive for the virus or negative for the virus. So positive for the virus, negative for the virus. And they say that the probability you test positive if you have the virus is 0.90. So that means 10% of the time you will test negative. And if you do not have the virus, there is a 0.15 chance of you testing positive, which means there is a 0.85% chance of not, which is not great. That's not a good not a good turnout for this particular test. Now, in my just what I like to do when I get these tree diagrams, I always go in and multiply no matter what, unless I'm like, it's only one question and I only am looking for one thing. That may be the one time I don't do it, but I'm just going to go ahead and say this branch is going to be 0.0036. This branch is going to be 0.0004. This branch is going to be 0.1494. If I multiply these two things, that's all I'm doing, and 0.8466. The one thing I'm going to point out, because I encountered this when I was doing it in my calculator, this 0.0004. When I typed it into my calculator, and I know I mentioned this before, but I'm going to mention it again, it gave me 4e to the negative 4, which basically told me that I needed to move my decimal place 3 spots to the left. So if I had 4, it's like 4 times 10 to the negative 4. It just basically tells you to move your decimal. So if you encounter this in your calculator, just make sure that you're moving your decimal, and especially on MATLAB, you're not typing in 4 because it will tell you it is wrong. So we're going to go in. Given that a person tests positive for the virus, that is going to be my first condition. Given that they test positive for the virus, what is the probability that they have the virus? So probability of having the virus given that they tested positive. So that means I need virus and positive over the probability of testing positive. So there are 2 instances in this particular situation where you potentially test positive for this virus. And that is here, where it's 0.1494, and here, where it is 0.03 or 0036. You have to consider all possibilities. So those are the 2 times where I get a positive result. So when I go in to find my denominator, I need to take 0.0036 and add it to 0.1494. All possibilities total go into an overall like marginal frequency. And then I'm only interested in specifically the probability of virus and positive. And so that is going in and doing 0036 on the top. Now, please, 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 please do not break my Algebra 2 teacher heart and cancel out the 0.0036s. You cannot do that. That is bad math. It doesn't work that way when you have addition and subtraction. Just want to cover all of my bases. So I would go in, I would take this into my calculator. If you're worried that your calculator is reading your decimals wrong or your parentheses aren't exactly lining up like they should, you can always get a fraction bar in your calculator by doing alpha y equals enter. And this is 0.0235. And personally, I know it's not a ton more thinking, but not having to do any multiplication when it comes to filling out these formulas is really, really nice. So that's why I always try to take care of it in the tree diagram itself. Now, the last one, what is the probability of a person testing and getting a false positive? So a false positive would mean that they have no virus and they tested positive. So just to kind of give you this, where this is coming from, they will sometimes use this language, which is why I picked this question and always include it. If I have the virus and I test positive, that is a true positive. Like that is what should be happening. The test is doing what it's supposed to do. But if I have the virus and I test negative, that is a false negative. So true positive, false negative. And on the same kind of thinking, if I don't have the virus and I test positive, that is a false positive. And if I don't have the virus and I test negative, that is a true negative, meaning I don't have it and I tested negative, the test is doing what it's supposed to do. So when they go in and they ask me for the probability of a false positive, I can also think of that exactly as what I have, as no virus and getting a positive. You don't necessarily need that second part that I wrote. I'm just doing it for the sake of, so we know where it's coming from. And all I have to do is go to my tree diagram and I see that this probability is 0.1494 and that is it. The only thing I will add on is if you have something that asks you to interpret, I don't overthink it. I literally rewrite the question and add in my probability. If I had to interpret this, I would just say the probability of a person testing and getting a false positive is approximately 14.94%. I usually convert to a percentage for sentences, but that is personal preference. So, tree diagrams, helpful. I probably can guarantee you'll know them when you see them.